让我放近一点。
这个玩意儿是咋涂的呀？啊？
你不知道咋糊了吗？
就这个玩意儿。
All right, good morning, everyone. So in today's lecture, we're going to go through a few examples in plasticity, just to explain how to calculate the plastic strains under various stress conditions. So let's just revisit what we talked about last time. In a uniaxial state of stress, I'm able to obtain a relationship between what I call the yield stress and a plastic strain parameter, which from a uniaxial state of stress is just sigma on 1 versus the plastic strain. Now from this relationship, I'm also going to predict when a material is going to yield in a three-dimensional state of stress, and also from this same curve, I'm going to use this parameter to predict what is the three-dimensional state of plastic strain in the material. Now to do this, I need a few functions. The first function is called the yield function. The yield function tells me whether a material is going to yield or not. And the yield function, according to the von Mises yield criterion, states that the material will yield 1 sigma von Mises minus the uniaxial yield stress, which is a function of how much plastic strain we have in the material, is equal to 0. If the sigma von Mises is less than the yield stress, then there's no yielding. Once it reaches sigma yield, we're starting to yield. The material is starting to yield and plastic strain is starting to develop. The amount of plastic strain developing depends on how sigma yield changes. So the amount of plastic strain developing depends on how much this is changing. So to find this, we use what we call the consistency condition. If this is what we call phi, then as the material develops plastic strain, phi stays equal to 0. Phi dot, which is how much phi changes with respect to time as the material is developing plastic strain, phi stays equal to 0, so phi dot equal to 0. Which means that as the von Mises stress changes, the yield stress will change accordingly. The von Mises stress changes because it has various, it's a function of the stress components, where there is a summation here, I equal 1 to 3. As the stresses change, the von Mises stress change according to this function. As sigma yield changes, the yield changes according to, I'm going to use D because sigma yield in this case is only function of the plastic strain parameter multiplied by the rate of change of the plastic strain parameter. Now there are two versions of this consistency condition equation. This is the rate version, or you can instead use the version where instead of epsilon p, the rate of epsilon p, you just use the change in epsilon p, delta E phi. this is approximate, and that's when you're integrating by hand. So as the stress increase or decrease, so each component is changing, you get the amount of plastic strain parameter inside the material is also changing. So this version is if you're doing calculations where you're calculating increments by hand, and this version is once you start, if you want to do actual integrations, if you have functions that you can integrate. And we will see different cases today. So this is the yield function, the consistency condition. So if I know how much the stresses are increasing, then I know how much the yield stress is increasing. If I know how much the yield stress is increasing, I know how much plastic strain parameter, or the change in the plastic strain parameter happens in the material. But that still does not tell me what is if it's a three-dimensional state of stress, it doesn't tell me how much plastic strain in the direction 1, 2, 3, or 1, 2. So I don't still know the direction, the plastic strain in the different directions. And that's why we need what we call the flow rule. Flow rule tells me that the components of the plastic strain in any direction, the rate of change of these components is equal to this the rate of change of that plastic strain parameter. I think I use P superscript, but right, I'm using P as a superscript in all these. So the rate of change of the different plastic strain components is equal to that equivalent plastic strain, its rate, multiplied by quotient phi, by quotient sigma j, which happens to be equal to 3 over 2 sigma monomesis Sij. And so if I know how much plastic strain parameter has the material has acquired, how much plastic strain parameter the material has acquired during that increment of the stress, or during that increase in the stress, and if I know what the actual stress is on the material, I can now tell you what epsilon P11 is. It's basically epsilon dot P11 is equal to 3 S11 divided by 2 sigma monomesis multiplied by this additional plastic strain parameter. Okay, so let's go through some examples. Now, in your assignment, first thing you have, the first question is you have to prove that if phi is equal to sigma mimesis minus sigma yield, where sigma mimesis is equal to the square root of sigma 1 minus sigma 2 squared plus sigma 1 minus sigma 3 squared plus sigma 2 minus sigma 3 squared plus, instead of 6, I'm going to put 3. Sigma 1 2 squared plus sigma 2 1 squared, and so on, divided by 2, minus sigma yield. Now I would like to get partial phi by partial sigma ij. You need to prove that this is equal to 3 over 2 Sij divided by sigma mimesis. So basically, this is sigma mimesis, which is function of the stresses. You need to make sure that when you differentiate this with respect to each of the stress components, you get 3 over 2 Sij, where Sij, if you remember, is equal to sigma ij minus sigma 1 plus sigma 2 plus sigma 3 over 3 delta ij. When I is equal to j, so basically S11 is equal to sigma 11 minus p, S22 is equal to sigma 22 minus p, but S12 is equal to sigma 12, S13 equal to sigma 3, and so on. So the problem in the examples that we're going to go through, 11.2.4.f, they're in your notes. The true stress versus true strain of a metallic material follows a bilinear relationship. With true strains of 0.002 and 0.25 corresponding to stress levels of 400 and 550. Young's modulus, E, is equal to 200 GPa, and Poisson's ratio is equal to 0.3. Now from this curve, you should know right away the relation, you should obtain the relationship between sigma yield and the plastic strain parameter. And notice that this slope, so initial slope, is equal to 400 divided by 0.002, which is equal to 200,000 MPa. What does this tell me? It tells me that up to the stress of 400, there is no plastic strain. In some other examples, I would give you a relationship between the stress and the strain such that plastic strain will start developing from the beginning, because sometimes it's easier to manipulate formulas if you have a relationship between sigma yield and epsilon p, that rather than starting from a the value of the stress here, it starts from a zero stress. At sigma equal to 550 MPa, epsilon elastic is equal to 550 divided by 200,000, and epsilon plastic is equal to 0.25 minus epsilon elastic. So this is 0.25. The elastic strain is this, and the plastic strain is the remaining part, and so the plastic strain is equal to 0.24725, and that's corresponding to a stress of 550. The slope of this material, this curve, is very important because in the consistency condition equation, this slope appears. Where's the consistency condition? I'm always interested in the slope of sigma I with respect to epsilon p. Now the slope depends on the type of relationship I give. In this relationship, the slope is constant. In another, if I give you another relationship here, the slope is not constant, it depends on where we are. So sigma yield is equal to 400 plus 150 divided by 0.24725 epsilon p and so h, which is the slope, is equal to 150 divided by 0.24725, equal constant only for this problem. It could vary according to what relationship we have between sigma yield and the equivalent plastic strain, or the plastic strain per atomic. Okay, so this is just set up the material curve that is given. So using the von Mises incremental plasticity, so this is the one follows the von Mises plasticity. Which means that sigma von Mises minus sigma yield equal to 0, that's the yield function we're using. Isotropic hardening means sigma yield is function only of only epsilon p, and that means, because next lecture we're going to study different types of hardening. This means if I look at the stress space defined by the principal stresses, and this is the radius of this is the radius, the initial radius, which is I think root 2 over 3 sigma yield 1. as the material develops plastic strain, it hardens, which means that the yield stress is higher. Yield stress is higher, that means that you will feel as if this material has become stronger in all directions. Because the yield stress in all directions has increased. Whether you pull it in the direction 1, 2, or 3, the yield stress has increased. And that's why we call it isotropic hardening. The material has hardened in all directions. So this is again the setup. Now what we want to do is find the volume. If a specimen, so we have three conditions. The first condition is a specimen is being pulled by sigma on 1. I want to find everything. The stresses, the elastic strains, and the plastic strains. If it's being pulled by sigma on 1, and epsilon to 2 total is equal to 0. I'm pulling the specimen, but I'm not allowing it to expand or contract in the second direction. In the third condition, I'm also going to pull it with sigma on 1, but having epsilon to 2 is 0 and epsilon to 3 is 0. So I'm confining the specimen, I'm pulling it from both sides, or fixing both sides, and I'm pulling it, and I would like to see the behavior. Now before we try to answer these three questions, just a lot of numerical, or a lot of formula manipulation, let's ask this. For the initial yield, which specimen will be stronger? Specimen 1, 2, or 3. We know that this, the initial yield, will happen when sigma on 1 is equal to 400. This we know, because this is a uniaxial state, and in a uniaxial state we know already that the relationship is once you reach 400, the material starts to develop plastic strain. So you're pulling, once you reach 400, the material starts flowing. If you confine it, do you think the initial yield, sigma of 1, will be higher or lower? And here, if you confine it in two directions, sigma of 1, will it be higher or will it be lower at the initial yield? What do you think? So let's look at this one. Who says higher? Who says lower? Who says the same? No response. Let the camera record show that there's no response. So, okay, well then let's wait until we actually solve it, and we'll see what happens. Okay, well let's start with the first one. Condition 1. Under uniaxial stress, I'm still going to follow the same thing that I will do in all these different conditions. And the first thing is yield function. functions state sigma hormesis minus sigma yield is equal to 0. That's when the material yields, but sigma yield is equal to 400 plus an upper. Before developing any plastic strings, sigma yield, the initial yield is 400. Now in a uniaxial state, the stress is equal to sigma 1, 0, 0. The hydrostatic stress is equal to sigma 1 over 3. The deviatoric stress is equal to 2 sigma 1 over 3. Negative sigma 1 over 3. Negative sigma 1 over 3. Which is equal to sigma minus p. Sigma hormesis, in this case, is equal to sigma 1. Material will not yield until sigma hormesis is equal to 400 is equal to sigma 1. So at sigma 1 is equal to 400, epsilon 1 plastic equals 0, epsilon 1 elastic is equal to 400 over E. Epsilon plastic ij, all the plastic string components are 0. Epsilon 1 elastic is 400 over E. Epsilon 2 elastic is equal to epsilon 3 elastic is equal to negative 400 over E, multiplied by the Poisson's ratio. And epsilon elastic 1 2 is equal to epsilon elastic 1 3 is equal to epsilon elastic 2 3 equal to 0. Above 400. What would happen above 400? As the stress increases above 400, partial sigma. So we have sigma hormesis minus sigma yield equals 0, which is sigma 1 minus sigma yield equals 0, because sigma hormesis in this case is equal to sigma 1. We're going to use the consistency condition. The change of sigma 1 dot minus sigma yield dot equal to 0. Partial sigma 1, or basically sigma 1, I'll leave sigma 1 dot. Sigma yield is equal to partial sigma yield by partial, or T sigma yield by T epsilon P multiplied by epsilon P dot. This is equal to 0. This is H. tells me that the plastic strain parameter is equal to H 1 over H sigma on 1 dot, which tells me that if I want to find the epsilon P, which is basically I would like to find the plastic strain parameter, is the integral of 1 over H d sigma on 1, where the bounds are from 400 to 550. So epsilon P is equal to 550 minus 400 divided by H. The different plastic strain components are equal to epsilon P dot multiplied by partial phi by partial sigma j So epsilon dot P 1 is equal to epsilon dot P multiplied by 3 over 2 Sij S11 is equal to 2 sigma on 1 over 3 sigma on means is equal to sigma on 1, tells me that epsilon dot P11 is equal to epsilon dot, the first component of the plastic strain is equal to the equivalent plastic strain. Epsilon, the plastic strain between 2 is equal to epsilon dot P multiplied by partial phi by partial sigma 2, which is equal to 3 over 2 sigma S22 divided by sigma hormesis, which is equal to sigma 1 S22 is equal to negative sigma 1 over 3 divided by sigma 1, which will be equal to negative over 2, which is what we would predict under a uniaxial state of stress. The equivalent plastic strain is actually epsilon, is the plastic strain in the direction 1, and the plastic strain in the direction 2 and the plastic strain in the direction 3 will be equal to negative half of that, and that's so that when we sum them all, we get 0. When we sum them all, then the volumetric strain, the volumetric plastic strain is equal to 0. So when we sum the plastic strain components, epsilon P11 plus epsilon P32 plus epsilon P33, they're always equal to 0, which means volumetric strain, volumetric plastic strain is equal to 0. And so if you want the relationship between epsilon on 1 and sigma on 1, epsilon on 1 is equal to sigma on 1 over E when sigma on 1 is less than or equal to 400. When sigma on 1 is greater than or equal to 400, it's equal to sigma on 1 over E plus sigma on 1 minus 400 divided by H. This is the plastic string, and this is the elastic string. So condition 1 is just basically, I already have the curve, I'm just recreating the curve based on what I already, based on the rules that we set. Now let's look at condition 2. Any questions? So far? Okay, condition 2. In condition 2, we have the following. So sigma 2 is not equal to 0. Sigma 2 is not equal to 0. You think? Do you think the material will start yielding when sigma on 1 is greater than 400 or when sigma on 1 is less than 400? It's the same question again. What's that? More? So who says more? Finally, people are starting to wake up. So okay, well let's see. How would we do that? How would we know? What's the condition then?
Stress.
What's that?
Make this deviatory stress.
How would you find the deviatory stress? Do you know sigma 2?
Well, it's negative mu. It'll be if this is tension.
What's the condition? What's the condition? What's this condition mean?
It'll be tension.
Right, and that's the how did you figure out that there's tension? What is the condition that made you think that there's tension?
Well, because the strain is restricted.
The strain, yes, that's what I'm looking for.
Yeah.
The strain is what's so this that's exactly what I'm looking for. Epsilon 2 is 0. Now we're still, let's say, since we already have an initial elastic stage, then that means the initial epsilon 2 elastic is 0. What does this tell me? That sigma on 1 over E minus Poisson's ratio sigma 2 over E is equal to 0. What does this tell me? That sigma 2 is equal to sigma on 1. Oh, I'm sorry. This is sigma. This is sigma 2 over E minus Poisson's ratio, which tells me that sigma 2 is the same as sigma on 1, but multiplied by Poisson's ratio. So this condition tells me that sigma 2 is equal to Poisson's ratio sigma on 1. As long as we're in the elastic regime, sigma 2 is always equal to Poisson's ratio multiplied by sigma on 1. So what does this tell me about sigma on 1 means? In this case, I have sigma on 1 squared minus sigma 2 squared, which is 1 minus Poisson's ratio squared, plus sigma on 1 squared, plus sigma on 1 minus sigma 3 plus sigma 2 minus sigma 3 Now we know sigma 33 is 0. Sigma 22 is equal to u squared. This is the von Mises stress. The von Mises stress is equal to sigma on 1 multiplied by 1 minus Poisson's ratio plus Poisson's ratio squared. So material will start to yield when the von Mises stress reaches 400, which means when sigma on 1 is equal to 400 divided by square root of 1 minus Poisson's ratio plus Poisson's ratio squared. Poisson's ratio is equal to 0.3. This will be equal to 450, around 450. So the initial yield will happen at a stress higher than the 400. Only because there's another stress. What's the value of the other stress? U sigma 1, which is equal to 135 MPa. So constant. Elastic strains Epsilon 1 elastic will be equal to 450 over E minus Poisson's ratio sigma 2 over E. Epsilon elastic 2 will be equal to 135 over E minus Poisson's ratio 450 over E, which should be equal to 0. Otherwise, I did something wrong. And epsilon 3 elastic will be equal to negative Poisson's ratio 450 plus 135 over E. Plastic strains are equal to 0 at this stage. At this stage, the plastic strains are equal to 0. Now, what we want to do now is calculate what happens beyond that initially. Assuming that sigma of 1 keeps increasing, and sigma, of course, and that means sigma of 1 Mises keeps increasing, which also means that sigma 2 keeps changing. I don't know how it changes, but it still changes because I still have that restraint. Now let's just ask this question. I want you to think. As you pull, now you start developing plastic strain. and you've kept that material, that restraint. Let's say you develop plastic strain, you develop plastic strains, you develop plastic strains, and then at some point you release all the restraints. You release that stress and you release that restraint. What do you think will happen? Will the material keep its thickness, or will it shrink, or will it get thicker?
Will shrink in direction sigma 3,3.
Okay, that's fine. I'm talking 2, 2.
It will stay the same.
It will stay the same. Okay, so, okay, what do you think?
Or if you release all the restraints,
Yes.
It's the same, the restraints act as the same as a tension load, right? So then it should.
But I released, yes, after.
Yeah, after you release, it'll get thinner.
Okay,
Not all the way.
what do you mean not all the way to the original? We started at the original, this is the original.
it will stay the same.
Oh, I see.
It's plastic.
There's plastic deformation, but you restrain it to the entire loading.
There's plastic, not plastic. Plastic, I don't know.
Yeah, that's right, there's plastic and elastic.
So elastic will go a little bit like, will sharpen a little bit, but still will be larger than the large motion.
So you think it's going to be larger?
Yeah.
You think
No,
you can
look, it's restrained the entire time. You release
Plastic
the
deformations happen only during the loading, right?
So I load it, load
Yeah,
it,
but
load it.
it will be that thickness when you.
What if it's not happening during the loading once?
Who said it's not happening?
Because it's restrained.
What's restraint?
Well, if we do
Yeah, right, just I'm asking the question. What is restraint?
strain in direction.
What is that? It's not, I'm not saying the plastic strain, we're saying the total strain.
I don't know.
So what will happen is that as you're pulling, you're developing plastic strain in this direction. You're developing a lot of plastic strain in this direction. You're developing opposite plastic strains in both directions. But in the opposite direction, in the direction that's restrained, you're elastically pulling it back. Once you release that, everything, it will go back, but the length is going to be longer, but it's going to be shorter in the other two directions.
So,
Yeah?
volumetric plastic strain is 0.
What's that?
So is the volumetric plastic strain 0?
Yes. The volumetric plastic strain is 0. But the restraint that we applied is not, we did not apply that the plastic strain is 0. We did not apply that the elastic strain is 0. What we said was the total strain in that direction is 0. Which means that the sum of the elastic component plus the plastic component is 0. There's always an elastic. There's always an elastic, the stress is not 0, therefore there has to be a plastic component that will cancel. Okay? Now this is what that's what the theory will predict. Now let's follow what happens beyond the initial yield if sigma 1 keeps increasing. Now I'm going to, you guys have all your notes? Have the notes? No? Can you? Or just I want to show you the curves. There's just that plasticity theory. Well, I'll draw them here. You can look at them at the phone. That's fine. Sure. So after we're going to do a lot of calculations, but let's show you the result right away. I just want to look at the results. This is what happens. Sigma 2 up to 450 is equal to Poisson's ratio multiplied by sigma 1. Once you reach that 450, you'll all of a sudden find that sigma 2 starts increasing, and then has a different slope between sigma 2 and sigma 1. So once you develop plastic strain, the elastic stress, there's no elastic, the stress in the second direction increases faster than sigma 1, and then after that, sigma to 2, the slope is different than Poisson's ratio. Of course, when you look at epsilon plastic in the direction 1, 1 versus sigma 1, up to 450 nothing happens. Beyond 450 you get a slope. As sigma 1 increases, you're developing a negative plastic strain in the second direction. Starting from 450, all of a sudden you develop large plastic strain, and this is negative, and these numbers are small. They're small because they're equal to the elastic strains, which are small. In the second direction, the plastic strains are equal to the elastic strains, and they're small. Plastic strain 3,3. Starting from 450, you'll get this slope. This is epsilon plastic 2,2. This is equal to negative epsilon elastic 2,2. Because their sum is equal to 0. And you can look at the rest. This is just the development of the elastic strains as functions of sigma 1. And the summation as well to give you you can sum the elastic and plastic to get the total strains. But how do we draw any of these curves? The fastest way is to run an abacus model, to be honest. You run an abacus model, you're going to get all these curves. And I actually verified all the calculations using abacus, just to make sure that I didn't do any mistakes in the derivations of these curves. I actually perhaps maybe verified that abacus have implemented the material model correctly, rather than verified my calculations. Anyway. Okay, so beyond 400, the material is still in a state of developing plastic strain, so phi dot is 0. Phi dot is equal to partial sigma 1 meses by partial sigma 1 multiplied by sigma 1 dot plus partial sigma 1 meses partial sigma 2 multiplied by sigma dot 2 minus h equals 0. The problem here is I know how much sigma 1 is increasing because I'm controlling sigma 1, but I'm not controlling sigma 2. Sigma 2 is changing to keep the restraint, the total strain in the second direction is 0. Find how sigma 2 changes, I need, now of course all these other numbers I have. This is partial sigma 1 meses, partial sigma 1 meses. by partial sigma on 1 is equal to 3 over 2 S11 divided by sigma 1 pieces. And this is 3 over 2 S22 divided by sigma 1 pieces. These are just functions of the stresses themselves. I'm just trying to integrate to see how these things change as I increase sigma 1. If I know this, it would have been straightforward if I'm also controlling sigma 22. So in some of the problems, I tell you that sigma 1 and sigma 22 are increasing linearly together. They're increasing linearly together, so you know you're controlling both rates. You can calculate this right away. But for these types of problems, I'm not controlling sigma 22. So you have to calculate sigma 22 dot from a different equation. And what's the other equation? Epsilon 22 total. The rate of development of epsilon 22 total is equal to 0. And what's this equal to? This is equal to epsilon 22 elastic dot plus epsilon 22 elastic dot. What's epsilon 22 elastic? Well, it's equal to sigma 22 dot over E minus Poisson's ratio sigma 1 dot over E. The plastic strains were following this flow rule. So I can replace it with epsilon dot E. Partial phi by partial sigma j is equal to 3 over 2 Sij divided by, this is 2, so we're talking about S22 divided by sigma 1 basis. S22 is equal to sigma 22 minus sigma sigma 1 basis. And now we have two equations in two unknowns. These are two ordinary. These are two differential equations. I'm going to write the other equation again. You need to solve those two equations by controlling sigma prime 1, sigma dot 1, 1. Sigma 1 changes from 450 to whatever value you want, 650. Sigma 22 initial condition is 150, changing to, I don't know, it's a function, and epsilon p dot, or epsilon p, changes from 0 to whatever. So using these initial conditions, and by controlling sigma 1, you can calculate, so I used mathematical to solve these differential equations, or you can do it by hand. To do it by hand, first you have to replace sigma 22 from both equations, and then you have a relationship. So cancel sigma 22 out. After you cancel sigma 22 out, you're going to have a relationship between epsilon prime and sigma prime. But even then, you will have issues. Actually, cancel epsilon p out first. find the relationship between sigma prime, sigma dot 1, 1, sigma 2 dot 2, 2, and integrate this to get the function of sigma 2, 2. After you integrate this, you can do it, then you can find epsilon p, or if you're doing this, so for this I used the numerical differential equation solver, or you can, if you want to do this by hand, instead of sigma dot, just replace it with delta sigma 2, 2. If you're not able to do the integration by hand, if you're not able to do the integration explicitly, this just make it into a difference equation, and that will solve it for you. So by knowing, you're just knowing that you're advancing in time just by controlling delta sigma on 1. Assume anything for, that's exactly what you did for the previous assignment. You assume something for delta sigma on 1, and then you can calculate delta sigma to 2 and delta epsilon, the equivalent plastic strain from those two equations. After you calculate those two, then assume a new delta sigma on 1. But all the other values, of course, all these values will increase because now we're at a different step. So you basically advance on the curve. Sigma 1 basis, or sigma yield, versus epsilon p. You're advancing on the curve. Okay, we'll give you 5 minutes and then we'll talk about condition 3.